I'm going to walk you through the information for the notion of a limit that's given in your textbook. This is on page 59. And it says that if the value of some function, which we're just going to call f of x, so this is just a generic function, if it approximates or gets close to the real number, okay, so I'm going to put in here the real number, L. Now, L can't be infinity or negative infinity, so we'll talk about the ideas of infinity, but L has to be a real number, so it's important. For x values close to but not equal to x naught, then we say that f of x, that f approaches L as x approaches x naught. The notation for this is we say the following. We say if x approaches x naught, then the function values, the f of x values, approach L. Okay, that's one way of saying it. The other notation is we say the limit as x approaches x naught of the function f of x is equal to L. So these are two different ways. Here's one way of writing it, and this yellow way is the more common way. Now, what does that mean? If we take a look at a picture, let's say we've got, let me draw out a coordinate system here, and let me put in a function. Now let's go ahead and talk about this. Let's call this f. This is the function f. Okay. And let's say this is 1 and this is negative 2. Let's say this is a height of 1. This is a height of 2. I'm just going to move this guy so that it falls nicely here. And let's say this is a height of 3. Okay. Clearly the green line is a function. It passes the vertical line test. Now let's talk about these different limits. So let's first discuss the limit as x approaches negative 2 from the left side, okay, of the function f of x. So as we come in towards negative 2 from the left side, what are the function values? What is the graph approaching? Now, we don't care what f at negative 2 actually is. We only care where this line right here is approaching. And it is approaching the value 1. So the limit as x approaches negative 2 from the left is 1. Now, let's look at the limit as x approaches negative 2 from the right. Well, if I come into negative 2 from the right, what happens to the height values? Well, they also get closer and closer to a value of 1. Since the limit from the left is the same, so this is from the left, it's called a left-handed limit, and the limit from the right, Since they are the same, then we say the overall limit as x approaches -2 of the function. Because they're both the same, we say that it's equal to 1. If they're different, we say the limit does not exist. Now, I want you to note here that the function at -2 is 2. Look, if I go to -2, the function's actually up at a height of 2. So one thing to note here is that the limits as you approach a value doesn't necessarily have to be what the function is at that point. That's why you can't just always go ahead and plug this guy in and see what you get out, because when you plug -2 in, you get +2 out, but the limit is 1. So that's what's important. See, this guy right here is not continuous, right? Because if I'm walking along this line, okay, if I'm walking along this line, I would fall through, or I'd have to jump up to get to that point. So there's what we call point discontinuity here. Okay, now let's go ahead and look at the limits over here. Let's look at the limit as x approaches +1. That's a really bad arrow. Let's redo that. As x approaches 1 from the left. So as we come in from the left, the function heights are getting closer and closer to the value 2. The limit as x approaches 1 from the right, that's coming in this way, these values are staying at a height of 3. Since the limit from the left does not equal the limit from the right, we say that the overall limit as x approaches 1 does not exist. Okay, there is no limit. So no limit. Okay. The function itself evaluated at 1 is equal to 1, or excuse me, is equal to 2, because it has a filled in circle there. So there's 4 different things you got to look for as we approach from the left, as we approach from the right, overall, and that what the function actually is. Now, there's some key notes here on page 59 that I'm going to write down. You need to have these memorized, and they need to be, part of your understanding of functions. Okay, note number 1 is that the limit as x approaches some number only depends on the values of f of x close to x for all x's close. Let me reword it like this. The limit as x approaches x naught of f of x only depends on the values of f of x as x gets close to, or as x approaches x naught, not at x naught. Okay, so we don't actually care what the function is at the exact point. We just care for values that are really close. Okay, the second part is it could be the case, so 2, it could be the case that the function actually doesn't approach a finite value. So here's what I mean. Let's say we've got our axis system and our function, so here's the value, x equals 3. And then our function looks something like this. Now we might ask, what is the limit as x approaches 3 of the function? Well, here's the problem. Yes, both sides are going to infinity, but this is not a real number. So we say that the limit does not exist, or we just write the symbol infinity, but we realize that this actually isn't a limiting value. It just describes the behavior of the function. So when someone asks you, if you have like a vertical asymptote like this, and someone says to you, what's the limit? Well, there is no limit, okay? Or the limit does not exist, because the limit has to be an actual real number. And that was what I was talking about up here. Where did I say it? Yeah, it said the real number, L. Okay, so limits have to be real numbers. The third rule is that when we're looking at the limits, as we approach some number, x naught, so here's x naught, we have to look at the limit from both sides. We can't just look at it from one side. So for example, if our function looks like this, you can't say, oh, well, I'm looking here and it looks like we're approaching maybe a height value. Let's say this is 1, this is a height value 2, and this is a height value of 3. Okay? So you can't say, well, look, I only have to look at it from this side, or hey, I only have to look at it coming in from this side. You have to look at it from both sides. So limits, the overall limit, which is really what we're going to be talking about a lot. Sometimes we look at left and right hand limits for continuity and things like that, but for the most part, we're going to be looking at limits from both sides. So we need to look at both the left and the right hand limits, and they must agree. So in this case right here, they both agree, so we get a limiting value. In this case, they don't agree, so there is no limiting value. Okay. The last piece of information that they give you here, which is a good thing to explain here, is that this is not a formal definition. So this is not a formal definition yet. There's ambiguity in it, and so what we need to do is we need to come up with, how the book says, an airtight definition, something that that everyone's going to agree on, that yes, this is how you explain limits, and also something that we can use to prove and to verify limits, not just saying, well, I made a table of values or I made a graph, because tables and graphs can be misleading. So, and in fact, for some functions, you can't even draw a table or a graph. Now, you can't write out the table and you can't draw the graph, is what I mean. So we'll get to an epsilon delta definition for it, and this is where a lot of students have some difficulty, because this is maybe one of the first times they've really seen a formal proof done. We'll talk about this very slowly when we get to it, but for right now, we're just going to use this argument above to look at the limits.